All right, welcome to The Explainer. Today we are talking about algorithms. You know, those invisible instruction sets that are running basically our entire digital world. We're going to explore how computers actually solve problems and, more importantly, why finding the right way to do it can mean the difference between something happening instantly and it being literally impossible.
Okay, let's start with a puzzle that I'm sure you've dealt with. Picture this. You're trying to find that one photo from a vacation you took last year. How on earth does your phone dig through thousands, maybe tens of thousands of pictures, and just pull up the exact one you want in a blink? Well, the secret, as you probably guessed, is a really clever algorithm.
So how would you even begin to tackle that? Well, the most basic way, the most human way, is to do exactly what you'd do with a junk drawer, right? You just check every single thing one by one until you hopefully find what you're looking for.
Now, in the world of computer science, this has a name. It's called a linear search, and the logic is about as straightforward as it gets. You start at the very beginning of the list, and you just don't stop until you either find the thing you're looking for or you've run out of stuff to check. It's super simple, and you know what? It's guaranteed to work, every time.
But, and this is maybe the most important question in all of computer science, just because something works, does that mean it's good? I mean, pretend photos, yeah, sure, who cares? But what about for 10,000 photos or 10 million bank records? All of a sudden, this simple guaranteed method starts to look painfully slow.
So what does good even mean when we're talking about an algorithm? Well, 9 times out of 10, it really just comes down to one thing: speed. And more specifically, it's about this question. As the problem gets bigger, how much harder does the computer have to work?
Okay, let's break that down into two scenarios. You've got your average case, right? This is where you find your photos somewhere in the middle of the pile. You end up checking about half of them. But then there's the worst case. This is when the photo is the very last one you look at, or even worse, it isn't in there at all. Then you have to check every single item. But notice, in either scenario, if you double the number of photos, you pretty much double the amount of work. It's a straight line.
But here's the thing. That nice, predictable relationship, double the items, double the work, that's not a rule. Some algorithms, they just get completely bogged down as the list gets bigger. The workload doesn't just go up, it absolutely explodes.
Just take a look at this table, which comes straight from our source material. Okay, follow me here. For a really small list, just 10 items, algorithm B is way faster. It's the clear winner. When we get to 14 items, they're pretty much tied. But then, right after that, things just go completely off the rails. At only 20 items, algorithm B is already taking over 1,000,000 steps. And at 50 items, forget about it. It needs over a quadrillion operations. I mean, that number is so big, our brains can't even really process what it means.
So look, the really crucial thing to get here is that we're not just talking about shaving off a few milliseconds. This isn't a small tweak. Choosing the right algorithm is the difference between a problem that your computer can solve in the blink of an eye and a problem that would literally take longer than the age of the known universe to finish. It's in a completely different league.
All right, so let's take this whole idea of efficiency and apply it to another classic computer science problem: sorting. You've got a list that's completely jumbled up. How do you get it into perfect order? This is like one of the most fundamental things computers have to do.
So one really intuitive way to do it is something called insertion sort. And honestly, it works exactly like how you'd probably sort a hand of playing cards. You kind of keep one side of your hand sorted, and then you pick up new cards one at a time, and you just slide them into the right spot.
Okay, let's watch how this works. We start with this messy list. First, we look at the 2 and the 5. We swap them. So now we have 2, 5. That part's sorted. Next up is the 4. We slide it in between the 2 and the 5. Now we have 2, 4, 5. Cool. The 6, it's already in the right spot, so we just leave it. Then comes the 1. Ooh, that has to go all the way to the very front. And finally, the 3 gets slotted into its place, and boom, the whole list is perfectly ordered. See? Simple. Methodical.
All right, now let's put our simple insertion sort up against a more advanced, more powerful algorithm called merge sort. And just look at the formulas here. Insertion sort's running time has that n squared in it. That's a quadratic growth, just like that slow algorithm A we saw on the table. Merge sort's formula is, well, it's way better. So this should be a total slam dunk for merge sort, right? Obvious winner?
Well, not so fast. Here's this really fascinating twist. Because insertion sort is so much simpler, it has less, let's call it setup cost or overhead. And what that means is that for small lists, and in this case that's anything with 43 items or fewer, that supposedly slower algorithm is actually faster. And this teaches us something so important. The best algorithm isn't always the most complex or powerful one. It's about picking the right tool for the job.
You know, this whole thing brings up a really cool question. Before we even write a single line of code to sort a list, is there some way we can just measure how messy it is? Can we actually put a number on the amount of chaos in that list?
Amazingly, the answer is yes. And the concept behind it is called an inversion. It's a really simple idea. An inversion is just any pair of numbers in a list that are out of order with each other. So for example, we all know that in a sorted list, the number 3 should come before the number 8. If you have a list where the 8 comes first, well, that pair, 8, 3, is one inversion.
So let's try this on the list we see here. We can just go through and spot the pairs that are out of order. Okay, so 8 comes before 6, that's wrong, so that's one inversion. The 8 also comes before the 1, that's another. The 6 comes before the 1, that's a third. The 3 comes before the 1, the 2 comes before the 1. You see, each one of these out-of-place pairs counts as one inversion. And if we go through and systematically count every single one of those out-of-order pairs in this list, we find there are exactly 5 of them. Now that number, 5, isn't just some random detail. It's a precise mathematical measure of how unsorted this list is. A perfectly sorted list, it would have 0 inversions. This one has 5 units of messiness. And here is the truly beautiful part, the hidden connection. It turns out that the amount of work our simple insertion sort algorithm has to do, the number of times it has to swap 2 numbers, is exactly equal to the number of inversions in the list to begin with. The problem itself literally told us how hard it was going to be to solve. It's incredible.
So after all that, what's the big takeaway? I mean, we started with a simple photo search, we talked about sorting cards, and now we're counting these abstract things called inversions. What's the point of it all?
Well, it means that computer science is so much more than just programming or telling a computer what to do. At its absolute core, it's a creative and deeply analytical way of thinking. It's about learning to look at a complex problem, finding the beautiful hidden structure within it, and then designing a truly elegant and efficient way to solve it.
So let's recap what we've learned. We've seen that picking the right algorithm isn't about being a little bit faster. It can be millions or billions of times faster. We also learned that the best algorithm isn't always the most complicated one. It really depends on the scale of your problem. And maybe coolest of all, we found that there's this deep mathematical structure hiding inside everyday problems, a structure that can tell us exactly how to solve them.
You know, this exact way of thinking is what powers some of humanity's biggest projects, from mapping the human genome to discovering new galaxies, which really leaves us with one final, and I think, crucial question to think about. What problems that seem impossible to us today are really just waiting for someone to discover a clever algorithm?